Okay, good afternoon, everyone. My name is Suraje Dessai. I'm one of the champions of the UK Climate Resilience Programme based at the University of Leeds. And welcome to our webinar series. It's my great pleasure to introduce quite a few speakers today. So we're doing a deep dive actually into a project called Future Drainage, that has utilized some of the state-of-the-art climate model information in the form of the UK Climate Projections 2018, particularly the convective permitting model, known as sort of UK CP18 local. And that model and climate information has been used to look at climate uplifts. So the type of information that you may need use for design of storm drainage and various other infrastructure. So I'm going to just tell you a little bit about some news regarding the program, but I'd like to first introduce our speakers now so that they could then actually go straight into their talk. So Future Drainage was led by Professor Hayley Fowler. She's a professor of climate change impacts at the School of Engineering at Newcastle University. Let's see if I can get this working. Yes. She's also a fellow of the American Geophysical Union and a Royal Society of Wolfson research fellow very recently. So she'll be introducing the project, and afterwards we have Professor Lizzie Kendon from the UK Met Office and Bristol University as well. So Lizzie leads a team of scientists that have been looking at utilizing very high resolution models to study climate change. And so you'll hear a lot more about UK CP18 local. Then we have Murray Dale, who is from JBA Associates. So he's a technical director there and has been working on water and hydrometeorology for almost 30 years. And he's also a chartered meteorologist. We'll have a little bit of Q&A on some of the climate projections, the user guidance. We'll have a comfort break, about 5 minutes, and then when we come back, we're going to look at surface water flooding. So besides Hayley and Murray, we also have Dr. Xiadong Ming from Loughborough University. So he's a postdoctoral research associate in flood risk assessment at the School of Architecture, Building and Civil Engineering. And then Hayley will share a Q&A there. So I think most of you will be very familiar if you've attended one of these webinars before of the rules of the game, but we'll have these presentations first, and then that'll be followed by the Q&A. So put your questions in the Q&A box at any time. Use the upvote so that you can vote for your favorites, and that'll put the question higher up in the ranking. Normally attendees are muted unless we enable that to happen. If we have time, we'll try to make that happen so that you can ask your question directly. And this is being recorded, so everything will be shared on the web. In fact, it's being live streamed, so it'll go straight onto YouTube straight after this. If you do have any technical problems, use the chat and someone here in the team will try to help you out. Yeah, use the hashtags and at will. So very briefly, a couple of quick announcements. We've been asked to promote this particular survey. UK Centre for Ecology and Hydrology is is doing a lot of work on the impacts of climate change on river flows for the program. Last week we had a webinar on that topic, the E-Flag project, and they have an online questionnaire to get a sense of the interest in databases and sort of formats and access of this type of information of climate impacts on river flow. So if you've got some time, do have a look at that survey. It only takes about 5 minutes, but it does close on Tuesday. So do have a go if you've got time. The other thing I wanted to make you aware of, there's a few spaces in the Greater London Authority. They're doing some climate risk mapping. So they have an online workshop where they're bringing together partners and stakeholders looking at social and climate vulnerability in new and existing projects, programs, and strategies. So if you would like to attend, this is happening on the 8th, in the afternoon of the 8th of December, do get in touch with Kirsten Gaida. There's the email there, and the link as well, I think, will be put in the chat as well, so you can have a look at this later. And the final thing is just some recently published paper. So Daniel Cottrell, Lizzie Kendon, who's here today, and other colleagues in the Met Office have just published some work looking at the frequency of extreme daily precipitation in the United Kingdom, particularly looking at the autumn season. And there's an infographic as well on the website, so where you can get a bit more detail on that. So without further ado, I will hand over to Hayley, who will introduce the Future Drainage project. So Hayley, I'll stop sharing my screen and hand over to you.
Great, thanks, Suraj. Right, I'll just share my screen. Right, hopefully you can all see that. Is that the right way round? Yeah,
that's perfect. Yeah,
perfect. So you can see the presentation version. Right, great. Okay, well, thanks very much, Suraj, for the great introduction. So I'm Hayley Fowler from Newcastle University, and there's a few colleagues from the Future Drainage project who are also going to be speaking today, but there's many more as well from all of the different partner institutions, and a few of which are able to be here to answer questions later as well. So it's quite a big team effort, and really the overall aim of Future Drainage when we set out was to be thinking about these type of storms that you can see there. So really thinking about these very intense, short duration rainfall events that cause impacts, particularly on surface water drainage. And to think about how new state-of-the-art climate models from the Met Office can actually contribute to updating guidance in this area. So as I've said already, it's a project that was very much a collaboration between different disciplines. And I think that's really nice in terms of bringing together climate scientists from the Met Office together with statisticians from the University of Exeter. We had hydrologists and engineers from Loughborough and Newcastle, and consultants from JBA as well, keeping us in line and making sure that we provide useful information. So really a collaboration between academia and stakeholders. And we really, Murray will say something about this later, but the idea really was that we actually did the work together. We put the proposal together with the stakeholders, and we really had stakeholder involvement from both the water companies and the regulators and others at every stage of this project to actually make sure that the revised rainfall uplifts that we were producing from the new state-of-the-art climate models from the Met Office were actually going to provide the guidance that was needed for urban drainage design and for modelling surface water flooding in urban areas. So we went from these UKCP local state-of-the-art climate models really through to these new uplifts. And of course, this is really important to many stakeholders out there in terms of water resources management, in terms of flooding, in terms of insurance, emergency services as well. And particularly thinking about both its contribution, the project's contribution, I suppose, to surface flash flooding and flooding in particular, and particularly of urban drainage systems, but then also thinking of the quality implications as well of increases in these sewage overflows, posing risks to public health and the coastal environment. So Suraj just kind of said some of this already, but we're going to split this webinar into two parts. Part one will cover the UKCP local projections, the method that we used, a little tiny bit on the method and the assessment of uncertainties. And Lizzie will also present some information about the new uplifts, which you can also find online. We actually released these in July this year. Murray will then talk about the guidance that's being produced to go together with these uplifts and the process of stakeholder consultation in the project, and also perhaps mention some work that's going on with the revisions to something called the REDUP tool, which is something used in the water industry to actually apply these uplifts. And then we'll have a time to discuss and ask questions about that part of the webinar before moving on to part 2, which will look at, we haven't presented this to anybody before, and it will look at the impacts of using these revised uplifts in sewer flooding. So in terms of flood risk projections for 6 UK cities, and we use these cities as really case studies here. They're examples of different size cities in different parts of the UK, so they're representing different potential climates, different potential changes, and different potential impacts, I suppose, from very small cities to very large cities. And obviously in this project, we weren't able to do a thorough job looking at the change to flood risk everywhere, but I think it gives us a flavour of some of the main messages that come through. So Murray at JBA is going to talk about the use of the National Risk of Flooding from Surface Water methodology together with the uplifts. And then Xiadong Ming from Loughborough will talk about the use and development of these fully dynamic urban flood models. And then we'll have some thoughts and recommendations on what should be used moving forwards. So I'll start with part 1. So we're going to talk about the future drainage rainfall uplifts in this section. And before I hand over to Lizzie, I just wanted to say something about the current UK guidance in this area. And I mean, it's clear that the UK guidance at the moment is quite disparate. It's quite different depending on which parts of the devolved parts of the UK that you're actually in. So there's guidance for peak rainfall climate change allowances from DEFRA from 2006, for example, for different time periods. There's guidance from the Environment Agency, but that's not been updated since 2011. And then there's some previous work that we did in 2017 for UK water industry research in the top right-hand corner there that has been taken up and used in Scotland. So Scotland have a kind of newer set of uplifts that we developed from a previous version of a convection permitting model in 2017. But what you can see here is that none of these current guidance look at different durations of rainfall or different return periods of rainfall. And most of them only provide percentage changes over very large regions. So it'll be interesting to hear your comments afterwards when we've presented this about some of the work we've been doing. And I'm hoping that you think that it's going to be something that is an improvement on the current UK guidance. So without further ado, I'll hand over to Professor Lizzie Kendon from the UK Met Office, who's going to talk about the UKCP local climate projections through to uplifts.
Hello, everyone. Thank you, Hayley. Firstly, I'll just to say a big thank you to Stephen Chan, who has done a lot of this work within my team. I'm very happy to take any questions on this at the end or during the chat. So if you put your questions in the chat, please, and I'll answer those as best I can. So firstly, I just thought it'd be very useful to give a background on what UKCP local is, for those who don't know. So this is a new set of climate projections using a model as detailed as that typically used for weather forecasting. So it has a 2.2 kilometre resolution across the UK. There are 12 members, and it's driven by a regional climate model that spans Europe. And indeed, the regional projections are also output for users if they wish to use them. And there's data for 3 20-year periods. I've listed them there, 1981 to 2000, 2021 to 2040, and 2061 to 2080. And these are for the high emissions scenario, RCP 8.5. Now, in July, we provided an updated set of projections, and that's what's being used here. And these projections are really important because they're allowing us now to look in real detail at climate change and processes and types of extremes that we haven't been able to give credible projections for in the past. In particular, summer storms, heavy downpours, hourly rainfall extremes, also severe wind gusts. And this information is at a scale that can be fed through to hydrological impacts models and flood models, as we are talking about here today, but also to look at climate change over cities as another area of work under the Climate Resilience Programme. So, Hayley, move on, please. So just to give you a sense of the different products here. So UKCP Local is one of a set of different tools that were released in UKCP 18. There was the probabilistic projections. There were also a set of 28 global projections with a 60-kilometre resolution. Then 12 regional projections with a 12-kilometre resolution spanning Europe. And then finally, these 12 UKCP local projections with a 2.2-kilometre resolution. And you can see on the top panel there, the different grids used in the different products that really highlights the increased level of detail that we're providing with these local projections. So this model is able to better represent the small scale behavior in the atmosphere, in particular convection. Convection is a key process behind many of our extreme weather events, and you really need the high resolution to capture it properly. This model is able to capture the influence of mountains, coastlines, urban areas. And you can really see how much we've zoomed in just here from this picture of London on the bottom right, which shows the area covered by a 12-kilometre box and how that zoomed in to 2.2 kilometres in the local model. And with this increasing resolution, we're able to now provide projections describing the types and extremes of weather locally over the coming decades. And that's a big improvement in capability from what we've been able to do before. Next slide. So in this project, we were principally interested in hourly rainfall extremes. And what this is showing here is really the underlying evidence establishing the credibility of these projections for looking at future changes. So what's shown here is return levels from 2 hour out to 100-year return periods. And so it's 2-year to 100-year return periods for hourly rainfall and for the different seasons. So we have spring, summer, autumn and winter. The black line is the CEH-GEAR observational data set. And then the red is the new CPM projections, the new 2.2 kilometre projections. And you can see for almost all seasons, the observations lie within the spread of models from the local ensemble. So that's the red plume there. And that is really important. In particular, it's able to capture the rate at which extremes increase with return periods. So the kind of shape of this curve is well captured by the red models, unlike the blue models, which are the regional 12-kilometre projections. And what you find in that case is, although the 12-kilometre model does a reasonably good job of capturing something like the 2-year return level, as you look at the higher ones like the 100-year return level, they are too high. So the rate at which extremes increase with return period is too strong. And this is really giving us a sense of which model is capturing the processes that are important for increasing extremes as conditions become favourable, which is obviously important for the credibility of projections in a warming climate. So based on this evaluation and others, we have good confidence in these projections. Now, briefly, I'll just talk about the methods that we've been used for calculating uplift. So uplifts here are the future changes. And we've used an advanced spatial statistical model that was developed by Ben Youngman at Exeter University. And that is allowing us essentially to fit all the data from all the different grid boxes across the UK simultaneously, which means that we can give a much more robust estimate of return levels. So we can look out to the 100-year return level with some confidence. We've also developed experimental method to try and correct for spatial and temporal correlation in the data, which is definitely not easy, but we have attempted to correct for that, which hasn't been done previously in other products we've released. And there are also 2 uncertainties here. So we have released information for a central and high estimate, but so just so you understand, that uncertainty is arising both from uncertainty in the extreme fit itself. So for each ensemble member, we calculate the return levels, if you like, and there is an uncertainty associated with them just purely due to the sample size we have. Also, there is uncertainty across the different ensemble members, which is due to uncertainty in variation of the driving model physics. And we kind of pull both these uncertainties together and then to give us a central and high estimate. I mean, this diagram on the right-hand side is essentially illustrating that. The dashed line is essentially showing us the uncertainty in a single member, in this case for extreme rainfall intensity scaling. And then you can see the colored dots are all the different members. So we combine this uncertainty in the dashed line from one with each of the members and to produce then the total uncertainty, which is shown by the black ellipse there. Next slide. So one thing it's important to recognize is that these projections do not sample the full range of uncertainty. So although they're giving us a real step forward in terms of now giving some preliminary estimate of uncertainties at these local and hourly scales, there is still aspects of the uncertainty that aren't captured here. And the first thing to recognize is that these projections only downscale Hadley Centre models that simulate relatively high levels of global warming. And I think this figure here on the right-hand side really illustrates that. This is showing mean responses for summer temperature, summer rainfall, winter temperature, and winter rainfall for Scotland and England. The black box and whiskers is the probabilistic projections. The blue dots are the CMIT5 models. The yellow dots are the Hadley Centre models, which are then downscaled to the regional models in pink and the local models in green. And you can see, particularly in summer here, we're only really sampling the warm and dry outcomes in the downscale projections. Also, unexplored uncertainties include uncertainties due to the emission scenario. So here we are using the high emission scenario RCP 8.5 only. So I think it's fair to say that the diagnosed uplifts can be seen as a relatively high case. Next slide. So here are some of the uplifts, the results here. This is for hourly precipitation. First of all, we've got the present day return level values, so 2-year, 30 and 100-year return levels. And then we have these low, central and high estimates of the change. So if we just focus in on the 30-year return level central estimate, Hayley, if you just zoom in the next slide. So if we zoom into that middle plot, this is the central estimate change for the 30-year return level. And you can see there's a UK average uplift of about 24%. And you can see that there's a north-south pattern here in the uplifts. And this is interesting because this contrasts to the present day pattern. So at the moment, we generally get higher hourly extremes in the south. This is basically a summertime convective phenomena. But then the uplifts actually show greater increases in the north. And we really understand this. It's due to increasing moisture being the primary driver of increased in hourly rainfall extremes. And in the south, particularly in summer, the increases in moisture availability are not as large as we see in the north. It's important to say that although this is the pattern of uplifts, actually we still see strong hourly rainfall extremes in the south in the summer in the future. Next slide. This is the 6-hourly case. Again, if you can zoom in, please, Hayley. So in this case, for the central estimate for the 30-year uplift, we've got an increase there of about 21%. And you can see that in this case, the spatial pattern of changes is slightly different. We have greater uplifts in the north and west. And actually, the present day return levels all show greatest values along the high regions in the west. And so that's consistent with increasing moisture, increasing the kind of availability of moisture to these regions where we're getting the strongest uplifts. And next slide, please. And finally, I'll just talk about the daily precipitation return levels. Interestingly, here we have lower uplifts compared to the hourly uplifts. So one of the things that Hayley touched on at the start is how the values here are varying depending on the accumulation period of rainfall. And definitely these results show that the uplifts are greater for hourly extremes compared to daily extremes. And if we just zoom in again into the central panel there, which is the 30-year return level central estimate uplift, we can see here that the UK average is 14%, and that compares to what the value was for the hourly extremes of about 24%. So it's a big difference. Also, straight away, you can see there's a very big difference in the spatial pattern here of the uplift. So for the hourly extremes, we had this north-south change in uplift with the highest uplifts in the north. That's not replicated here. And essentially what is happening here is daily extremes are generally a late autumn, wintertime phenomena, whereas the hourly extremes are convective summertime phenomena. So the processes are very different. And here in wintertime, we see increases in moisture availability right across the UK. And so the increases here are basically driven by that and also changes in large scale circulation patterns. So that explains the slightly different spatial patterns we have here. So I think it's important to say that these uplifts vary with the accumulation period of rainfall. They also vary very much spatially, as you can see here. And with that, I'll stop there, and I'm happy to take questions at the end and move on to Murray. Thank you.
Thank you very much, Lizzie. I'm a technical director at JBA Consulting, and I've been working with Lizzie and Hayley in this project and on previous projects in the last 10 years or so related to this same issue of how rainfall intensities may change in the future. So it's been a very important period to be involved because of this advent of the convection permitting model that has been for some time now, being able to simulate changes in the type of rain that gives us the intensities that cause these problems in an urban context in particular, but wherever we get surface water flooding or issues related to urban drainage. So I'm going to talk a little bit about the guidance that we produced that was for users of the outputs from future drainage, and we can cover some questions afterwards if there are any. Next slide, please. The guidance and uplift shapefiles were released on the 22nd of July, and this is an image of a 6-page document that you can access via that web link, which is on the screen there. This guidance was designed to be understandable to people who might be wanting to apply the guidance. So it's written in relatively non-technical language, as non-technical as maybe you can get in this area, because obviously there are some technicalities to consider. It details how to access the uplift shapefiles so that the results are presented in GIS shapefiles, so that you can see the amount of uplift that affects different parts of the UK in that way and load them into a GIS system, which can be overlain with different layers that might affect specific assets or parts of the country. It talks about the format of the output and how to apply the uplifts, and it also makes a broad comparison with the previous project that was funded by UK Water Industry Research and was published in 2017, where there were some uplifts that came out of that, and Hayley mentioned that a little earlier. Next slide, please. The headline messages then are somewhat covering over what Lizzie's just pointed out, but just to say that, and the guidance makes this point, that the uplifts are varying by location, but they're also varying by event duration from 1 to 24 hours. They're varying by return period or return level. So in the image on the right, you've got the 1 hour and 24 hour comparisons that Lizzie just showed to give an indication that they are varying by event duration. And they change as we go further into the future. So we produced uplifts for 2050 and 2070. 2070 is a midpoint in the furthest ahead of the time slices for which the data were available. 2050 is a key date for the water industry, who are designing urban drainage systems that need to be resilient to that date. So the uplifts that we derived for 2050 are an interpolation between the two time slices of 2020 to 40, or 21 to 40, and 61 to 80. So a midpoint there is 2050, and so we interpolated to get those outputs. And as Lizzie's mentioned, a central and upper estimate of change have been provided based on the amount of data we've got, which gives us some handle on the sort of reasonable worst case and a central estimate, which can be used for planning purposes. Next slide, please. Hayley mentioned that we consulted a lot with stakeholders on this project, and I'm very grateful to those water companies that put forward letters of support into the proposal, and there's a list of those water companies and their letters there on the right. We also got support from SEPA and the Met Office, and once we got the project underway, the Environment Agency were also keen to be members of the stakeholder group, and they also were important in contributing to the decisions that we made early on in the project about how the outputs would be defined. So we ran a stakeholder workshop in September 2019, shortly after the contract award. There's also a paper that I presented at the SIWEM Urban Drainage Group annual conference in November of that year, which is where you commonly get between 100 and 300. I think in fact this year we got 450 attendees at the virtual version of this conference. And I made a presentation of this project at that event just a couple of weeks ago. So that's a very good place to be engaging with urban drainage stakeholders, because a lot of folk attend that event. And so there we talked about the outcomes from the September stakeholder workshop, and we agreed that we would derive rainfall uplifts that supersede the UPWIR project, that there would be a difference in the regional groupings, and I'll talk about that in a minute. We defined the 2050 important time horizon and how we would address that, because it's important for the DWMPs that the water companies are required to produce, and define some useful return periods going up to 200 years. And in fact, 200 years was presented a challenge for us with the data, but that was an objective that we set ourselves. But we've got results for up to 100 years, and recommend that if you're going to 200 years, you can use the same as the 100-year results, because that's probably less uncertain than deriving values for that 200-year point. Next slide, please. So I mentioned that the regionalisation was an issue. In the 2017 work that was done for the water utilities, although the outputs were also adopted, as Hayley mentioned, by SEPA, we effectively divided the country into three, with those sort of put bold yellow lines to illustrate how those were divided up. So we called those Northeast, Northwest and Southern UK. And we provided uplift values for those three regions. The water industry found that when they were using these uplifts, that they were getting, some of the companies were separated by those divisions. Severn Trent, for example, Scottish Water has a line through the middle. So we took it on ourselves in future drainage to improve the regionalisation. And we came up with two options for doing this. One was to have uplifts that vary by 5% by water company region. So that's option 2 in that text, as opposed to option 1, which was to simply show the uplift variations with a 5% increment wherever they lie across the country, so not being informed by any river boundary or water company boundary. We put this to a vote to those people who are involved in our stakeholder group, and of those who replied, we got seven out of 9 who indicated that they were more keen for a regionalisation that was not split by any local, ground-based regional divisions, but simply was the way that the climate model output it. So we did identify, for example, for United Utilities region for the northwest of England, that there was a variation in the uplift between the north and south of that part of the country. And so that was particularly for companies where that affects their, where they are seeing that change, they were more keen to see the uplifts vary by the way in which the climate model showed they would. Next slide, please. So the guidance tells you how to access the uplifts. You first register with the CEDA archive. You then download the shape files that you need, and you can highlight them in a GIS platform, whichever one you're using, so that you can select the one that's appropriate. So that example there shows uplift 50, that's the 50th percentile, and that relates to the central estimate. 95 would be the high estimate, so the one below that, and the guidance explains how you access that. Next slide, please. When applying the guidance or the uplifts by these regions, if you plot these out in a map format, you see how they vary by well, they're varying, as we said, by return period and duration, but in the regional variation, you can see some quite sort of fine levels of detail. Now, we intentionally didn't want people to say, well, if just this one cell shows it's 5% higher than the neighbouring cells, that we should put too much attention on that. So because there's obviously uncertainty in the outputs, our recommendation is that you don't use individual cells to define the uplift level for the location you're in, but a group of regional cells that gives you the general picture of the amount of uplift you're experiencing. So there's some text there taken directly from the guidance that explains that point. So for example, I think we make the point there that rather than use an individual cell, consider an area such as the Lake District as a whole and what the values are across that region. If you happen to be landing between 2, then you can take a midpoint, say between 25 and 30%, or you can be precautionary and use the 30% uplift in that example that's put forward there. We also recommend that you justify any option that you take so that it's written through in an audit trail of how that's done. Next slide, please. It's also worth pointing out that the uplifts are designed to work with a baseline data set. So the current baseline, if you like, is the FEH13 depth, duration, frequency data. If you're used to flood risk investigations where you're using the flood estimation handbook, FEH, you'll be currently using the FEH13 rainfall data set. We are aware, I've just only heard this week, that the update to FEH13, FEH22 will be released next spring. So that will be effectively put forward a new baseline. Now, we propose that the uplifts are applied to the current DDF data set, FEH13, because they're similar to the baseline period that the climate model was run over. If your users are going to be making use of the FEH22, then there may be a need to make some adjustment based on that slightly changing baseline. So we can potentially put forward some suggestions about how that can be done, but I think it's it can be seen that there'll be some climate change already between FEH 13 and 22 affecting the rainfall around the country. Next slide, please. So lastly, we got some comparisons here with how these new uplifts from future drainage are compare with the work from the UPRIS study, and also how they compare with those with Environment Agency and SEPA guidance, which is in existence at the moment. So I guess these slides, I hope, can be made available, or people can refer back to them. But this information is also provided in that online guidance. The table to the top left is effectively showing that they're pretty high estimates in the northwest of the UK, particularly the more, not the central estimate, but the high estimate, the 65% value there is coming down quite a bit with future drainage. We've got ranges from and to with future drainage because these differ depending on the duration, particularly of the rainfall you're looking at. Whereas in the previous guidance, we gave values for all durations, 1 to 24 hours. So there's a slight reduction there in Scotland and the northwest of England, the far northwest of England. But there are also some slight increases in the southern part of the UK. So the central estimate of 15% is now ranging between 20 and 25%, for example. And those, when you compare them with the existing guidance, indicate that there might be some higher rates of change when you compare them on the national scale to that table on the right that shows the central and upper end uplift estimates for the 2050s. So the 10 and 20% there from the Environment Agency, that central and upper end may well be worth increasing, but the Environment Agency, as we understand it, is taking on board some of this output and deciding how to make use of it in updated guidance, which I understand will be released in the second half of next year. I think that's probably all I want to say. Thank you for putting the conclusions up. So this is the last slide in this session of the webinar. The uplifts for short duration extremes are higher than the 24-hour uplifts. So that's one generic conclusion we can make with all the outputs so far. The spatial pattern of current return levels are different to the uplifts. The spatial pattern of uplifts differ between different durations, and in many locations, future drainage uplifts exceed current guidance. Particularly, I would say, in southern England, that is, or southern and central England and parts of Wales. Okay, thank you, Hayley, and we'll be happy to answer questions between us if there are any.
Great,
Okay.
Thank you very much, Murray and Lizzie and Hayley. There have been quite a few questions in the Q&A. Do keep them coming. Our Met Office colleagues have been very efficient at answering them, so they've moved tabs from the open to answered. So do have a look at them. But maybe Stephen and Lizzie, if I may, I mean, I might ask, just get a bit more of airing of that first question about stationarity, because I think it is quite important, and it'd be good to hear whether Murray's got some views on that. So, sorry, we don't actually have the name of the person who asked the question. It's anonymous, but effectively that person is saying, you know, if we're talking about a non-stationary system here, a changing climate, to what extent should we be using the concept of return periods? And so, yeah, I don't know if you want to kickstart, Lizzie, on that.
Okay, yeah, I mean, so firstly, just to clarify what we did here in the methodology. So we have assumed stationarity of the climate between each of the 20-year periods. So we haven't got any covariates, as it's called, any variation with time or global mean temperature or something like that. And that is an approach that can be done and could be done in future potentially. But here we make, I think, a reasonable assumption that during each of those 20-year periods, that the stationarity. The difficulty comes, I guess, when we start to communicate this to other people. So we're saying, well, this is the 1 in 100-year return level uplift for 2050. Well, actually, that is only valid at that time. So it doesn't mean if we were to look out from 2050 for 100 years, then on average it would occur once, actually, because obviously the climate is changing. So I guess maybe that is something we need to think carefully about, particularly when we're talking about such long return periods. And I think, I guess, trying to explain to people what actually that means. It means, on average, it would occur once every 100 years, but that doesn't mean it'll only occur once in 100 years. And in fact, and things are changing. So actually what you would actually see as time evolves will be different. I think it's still a useful concept here for feeding into the analysis that has been done in the past. Obviously, historically, we've used return levels, but I think it's right to raise it as a communication issue, and we need to be careful what we actually mean.
Great, thanks, Lizzie. I wonder whether Murray and Rob have got some practitioners' perspective on that, or Hayley, whether you want to come in on this.
I mean, I'm sure that Murray will say the same thing, but I mean, I guess the thing is that it's what's used in practice. So at the moment, people design to certain return periods. So we kind of have to fit in with that. I'm cognizant, though, that yeah, absolutely, things are changing, but there isn't, I don't think, anything out there at the moment that people are going to are using as an alternative. So when an alternative comes up, we can kind of switch to that, but I guess it's just what's used in engineering design, and it's perhaps something we need to rethink. Murray?
Yes, I was going to say the same thing. I think this question came up in the CIREM UDG event last week, so I'm not sure, 2 weeks ago, if the questioner is the same person, but one of the responses to when that came up in that conference was that one way of improving communication can be to use annual exceedance probability instead of return period. So instead of saying 100-year rainfall, you talk about the 1% probability rainfall. Now that may help with some public communication and other things, but in the engineering and design world, the return period concept is still very much in use and understood by the engineers and designers, even though it may not be well understood by the public, for example. But yes, it's true that it's very difficult to move away from this concept of the design storm and design rainfall, because we're still using the FSR and FEH methodologies from 1975 that haven't changed. What I would say, though, is that there is more interest now in continuous simulation of rainfall and flow to assess flood risk in catchments and urban drainage catchments, so fluvial and urban drainage. So there are more than one ways of assessing flood risk. It's not just with a discrete event and uplifting it with a fixed percentage like this project has given you the opportunity to, but also to uplift your whole time series of rainfall and to run that through simulated catchment models that also simulate changes in land use and other effects that might be happening in the future. So yeah, those are the points I've made. But I agree with you, Hayley.
Can I just add to that, Suraj? I think that's right. Might be worth noting, many people on the call may be aware of the interim guidance on non-stationary flood frequency analysis methods that was published not that long ago on .gov.uk. So there is guidance, methodology, and there are some tools that have recently become available to support the industry in applying non-stationary statistical methods for extremes. Most of what's been done there, I think, has been geared towards river flow estimation. But I think, to my mind, it's not quite clear yet how that type of analysis should be used. But if we are going in that way, I think the concepts of return period and return level, they may still be useful, but we're going to need to get used to providing much more information about the frame of reference when we use those ideas. So, things like the date at which a return period or a return level is being evaluated, or the period over which a risk calculation is valid.
Great, thanks, Rob, and everyone for answering that question. Things are moving fast here on the question and answer, so I'm losing track of it, but maybe I'd like to pick up on one that you have answered, Lizzie, because I think it'd be of broader interest. So the Hadley Center model you sort of demonstrated was warm and a bit drier. So Chris Parker was asking about whether you plan to run some other GCMs, some wetter GCMs, and sort of coupling that with an RCM. And maybe I'd broaden that out actually also to think about, are you going to consider other RCMs? So within the program, UCL is analyzing Eurocordex for the UK. So I have plans to add more GCMs and more RCMs and in future analysis to explore the uncertainty space.
Hello, yeah. So we certainly have plans for downscaling other global models with our regional and convection permitting model. So in fact, we have simulations running at the moment, which are downscaling some of the CMIP5 models, which I showed in that diagram there, which are sampling quite different changes in summertime in particular, and that were within the set of global UKCP18 global projections. So we are downscaling that, and that is something we very much recognise, and that we're hoping to provide that data to users towards the end of 2022. In terms of the other thing you raised there, Eurocordex, that has been something we have considered as well. I think that is more difficult to do. How we would need to carry out a evaluation of the different Eurocordex models, just as we have done for the different CMIP5 models, to make sure they adequately represent key climate variability and other metrics, so that we have confidence in them before we then include them in the set. So it's not a straightforward case of just including them all. It is something that we've considered, though. Whether or not we have the resources to be able to do that properly and integrate it within the set, I think, is still uncertain, amongst other priorities for UKCP Next, but it has been recognised as something that could be very useful. I would say that it's not just the RCMs, actually. There's a multi-model ensemble of convection permitting models, and one of the Cordex flagship pilot studies, and also the EUCP project, which similarly could be brought in to the set here. So we would be sampling different versions of different regional models and different convection permitting models, rather than just the perturbed physics members here. But certainly a definite step forward in this will be us downscaling different CMIP5 models. So yeah.
Thanks, Lizzie. And just as a quick follow-up, because Chris has asked a follow-up question, which is very relevant, actually. And I know some of your colleagues, Helen Hanlon, Dan Burney, and others have done this type of analysis. So do you think you could convert what you folks have done to look at this as global warming levels, rather than, so at the moment you've got the highest RCP, if I understand correctly, forcing the UKCP 18 local, but Chris is mentioning TCFD, for example, and there's a whole bunch of scenarios there, 1.5, 2, 3, 4 degrees global warming. So is there an easy way to translate that from what you've got now?
So, well, obviously you can back out warming levels to some extent. We have the global evolution of temperature associated with our RCP 8.5 run. So you can pull out information, I guess, for time periods. And I should say that we are actually carrying out simulations that fill the intervening time slices. Those are still running nearly complete. So we will have data from 1980 right out to 2080 for the convection permitting model as well, from which obviously there's a fully transient time series from which we can presumably use methods to pull out different global warming levels. I appreciate that kind of how you achieve a global warming, the rate at which you achieve that, and the path to it can have important consequences for the local changes. Obviously, that's something we couldn't analyze with these simulations, but certainly there's a lot of discussions underway at the moment in terms of, and we'll be moving forward in terms of what scenarios we might want to do for UK CP8 next, whenever that may be. And I think there's definitely an appreciation that we may well need to be doing more than one scenario to try and answer this. And I do appreciate the real importance of translating this information into global warming levels as much as we can.
Thanks, Lizzie. And linked to that, Adrian Lee was asking you, Murray, to explain a little bit the lower emission scenario, because I think the note from Acquia says it makes very little difference. So could you explain to Adrian a little bit why that's the case? So up to 2040.
Yeah, so that this choice of RCP 8.5 is Lizzie can explain well as to why that's been done in the choice of which emission scenario was used in the high resolution model. But on this point where I've circulated a note from some meeting minutes from an ongoing project for Acquia that Adrian's a member of, where I pointed out that the emission scenarios don't make much difference to 2040. I've got a plot here, which if I can share my screen, will illustrate that UK mean temperature anomaly shows that all emission scenario pathways, the RCPs, are quite close when it gets to sort of 2040, but it's only beyond 2040 that they start to diverge somewhat, particularly RCP 8.5. So that's why I made that statement about 2040. This is temperature and not rainfall, but temperature and rainfall intensity are very closely linked. And there is a relationship that's been well observed, a Clausius-Clapeyron relationship, it's termed, that relates temperature increase with increase in relative humidity, which can be directly translated to rainfall intensity. Lizzie and Hayley are more specialists on this subject than I am, but I think that it's worthwhile pointing this out, that while there's concern that RCP 8.5 may be the highest of the RCP scenarios, that it's unlikely to be making a great deal of difference at the 2040 and probably 2050 scale, although it might be starting to show at 2050. I can invite Hayley or Lizzie to add anything on that.
Yeah, I mean, I think I don't have anything particularly to add. I think that you covered that very well. Yeah, I mean, it doesn't really matter which RCP you look out to 2040, and that's quite obvious from your plot there, Murray. I think I think perhaps different decisions might be made next time these type of scenarios are run, as Lizzie said before, dependent on the sort of commitments that are made by the COP process. For example, additional commitments were made just 2 weeks ago by different countries that should hopefully mean that we don't reach that RCP 8.5 warming by the end of the century anymore, and perhaps we'll be wanting to think about looking at some of these slightly lower RCPs next time.
Thanks, Hayley. I think I'll just take one final question before we have a comfort break, and this is from Shirley Greenwood. Have you folks got any other plans to look at even rarer events? I think 1 in 200 scenarios. Sorry, there's a 0.1%. I'm not sure what the unit is referring to. Maybe someone knows. But beyond what you've already produced, are there any plans to look at even rarer extremes?
I can answer that if you like. I mean, we had some discussion out in terms of what return level we were comfortable providing information for, and we felt we could justify using the current methods to go out to 100-year return levels. But I think 200 years and beyond, we felt was going to whether the uncertainties were such that we didn't feel that with the current data that was something we could do. I mean, I guess potentially the way we could go to higher, more extreme events is maybe starting to exploit the full transient data and fitting non-stationary extreme value distributions to that. So using data from all 100 years and rather than the 20-year time slice approach that we've used here. That is one method we could do. Otherwise, obviously, we're in the situation of needing to run more ensembles, I guess, to look at that. So that is something we did discuss, and we don't feel with the current data anyway we can go beyond the 100-year return level.
Okay, thanks, Lizzie. Yeah, go, Murray. Yeah, by the way, Shirley does add, 1 in 1,000, which
I just wanted to point out, if I could, Suraj, thanks, that there's an ongoing project that the Environment Agency is managing related to probable maximum precipitation and probable maximum floods, which are a engineering design concept that are used in particular for reservoir safety, but also for other water bodies or highly vulnerable locations. So that this is a concept that's been around for quite some time, but it's a method for testing the safety of reservoirs, which have to be safe to events much higher than 100 years. And so there's a research project ongoing that is looking at this, and one of the options is the use of high resolution climate models, which are at the same resolution as weather forecasting models, to see whether there are opportunities for estimating PMP, probable maximum precipitation, using such tools. But it's at a research and early stage, so I can't really say much more than that at the moment on that point.
Okay, thank you very much, everyone. I think in the interest of time, we should have, we've gone for an hour, we should have I suggest we have a 5-minute break. I mean, if colleagues are able to answer some of the questions that are remaining, as you have done so well, thank you. I mean, go ahead, please go ahead. But I suggest we reconvene at 7 minutes past 2 to hear about the second part of the webinar. So I'll see you all in 5 minutes, but thank you very much. Okay, welcome back, everyone. Let's, I think, restart part 2 of the webinar. So I'll hand over to Professor Hayley Fowler from Newcastle University. Over to you, Hayley.
Thanks, Suraje. Right. Screen. Right. Let's try this. Is that the wrong way around?
That's the wrong way around, yeah.
There we go.
Yeah, that's it. Perfect. Thank you.
Right. Perfect. So, thanks everyone for all of those really interesting questions. If you don't feel your question has been adequately, I suppose, answered, then please do feel free to put the questions into the Q&A again, because we'll have another discussion section after this part 2. So we're going to be talking about the impact of the revised uplifts on sewer and surface water flooding in this next section, which was the other objective of the project, to really test out these new uplifts in flooding models. So just to give a little introduction to this before I hand over to Murray and then Xiadong, we aimed to compare different outputs from different methodologies in this section of the project. So JBA ran some models using the risk of flooding from surface water methodology, which is efficient enough to apply nationally, but makes some simplifications, particularly to infiltration rates and things like that, which are picked up proper and dealt with perhaps in a more sophisticated way in the detailed hydrodynamic models that Xiadong has run for the same 6 cities in the UK. And the idea of doing this this comparison was really to look at whether the detailed physically based models gave different predictions of changes from the RoFSW methodology, and to give some advice to users about what was needed for surface water flood predictions for future design. So without further ado, I'll hand over to Murray, who's going to talk about the risk of flooding from surface water methodology that JBA have been applying.
Thank you, Hayley. I'm going to talk for 10 minutes, or hopefully no more, about the approach we took with this in JBA, so I'm covering it quite quickly. The work was undertaken by specialists in JBA who have undertaken the risk of flooding for surface water flood mapping for the Environment Agency, and in particular I'd like to acknowledge the support of Vicky Crowley, who's helped a lot with this, but also Rob Lamb, who's on the call, and Neil Hunter from JBA have been involved and are well familiar with the approaches taken. Next slide, thanks. The risk of flooding for surface water has this abbreviation, RoFSW. This approach is the Environment Agency's national mapping approach that was used, and it's comprised of local model output data where these are available, and 2-meter J-flow broad-scale modelling everywhere else. The 2-meter J-flow modelling is also known as the UFM FSW, which stands for the Updated Flood Map for Surface Water. So it's, if any of you are familiar with that acronym, that's the approach that's been used. So there's an image there showing some of the outputs from one of the locations we did this on in Carlisle, in the northwest of England, and I'll talk a little bit about some of those results in a minute. Next slide, please. The study locations we looked at were these in both the JBA team and the Loughborough team. They were chosen to be different parts of the country, different climatologies, but all urban areas, all areas at which surface water flood risk is a known issue. We didn't cover in JDA, we didn't cover the location in Scotland, Glasgow, which was covered by Loughborough, because we were using the Environment Agency approach, which is for England. Next slide, please. So we prepared these various tables for these locations, where we've got the city locations that we have picked and the degree of uplift, the percentage that we would be applying to 1, 3 and 6 hour rainfall events. So those were used in the modelling approach. And these were done for the 30-year and 100-year return periods. So the tables show the percentage uplifts used for each of the model simulations. Next slide, please. The model setup, this allowed the outputs from this element of research to be directly comparable with the risk of flooding for surface water mapping. And there was set up an input from the urban flood map for surface water model. So that same model approach was retained. The FEH 99 HIETA graphs, that's the rainfall profiles, were taken directly from the updated flood map for surface water model. And it's these HIETA graphs that were adjusted to represent the climate change using the percentage uplifts. The use of JDA's in-house modelling software, JFlow, uses shallow water equations, and so that approach was retained. So there are some other facets of the model approach that was misused in this case. I can talk about HIETA graph loss and runoff, but in fact that's a relatively simple approach that applies a consistent amount of loss to the urban drainage system and assumes that that's realistic. So it's not perfect, obviously, so we're not modelling any of the underground sewer system explicitly. Next slide, please. Right, to obtain the values for each grid cell in the model, we apply this pick grid method. So on the completion of the modelling, the raw output grids were post-processed to generate a single grid for each return period and epoch. To do this, the 3 storm duration grids for each scenario had to be combined to generate the worst case scenario for every modelled cell. For this processing, the pick-on hazard method was used. Hazard in this case is a function of depth and velocity of water, so it considers those 2 facets to derive a hazard value. So those hazard values are derived from the range from low to a low hazard, which is where caution is urged, right up to danger for all, including emergency services, where hazards are high, either because the velocity or the depth is very high. So there's an approach by which this pick grid works. Firstly, the maximum hazard grid is created by taking the maximum value of each cell from 3 storm duration hazard grid cells. Secondly, the pick grid is created by analysing which of the 3 individual storm duration grids the maximum hazard value has come from for each cell. And thirdly, the pick grid is then used to pick the source of each cell to create the maximum velocity and maximum depth grids. And that is the approach that's consistent with the Environment Agency risk of flooding for surface water map. Next slide, please. So that's the hazard grid that I mentioned, which has come from DEFRA research in order to determine these velocities and depths that give you different types of hazard. A hazard index threshold of 0.575 was used to determine whether cells were considered wet or dry and therefore filtered out or retained in the output. The thresholding value is in line with the risk of flooding for surface water mapping. The red patches in this figure show an example of the speckle in and an uncleaned outline, with the blue showing the final cleaned outline. So this is a method to sort of error correct the output by making sure that individual cells are removed so that it doesn't create this sort of noise in the system. Next slide, please. Here's some results for the 100-year return period case in a part of Carlisle. This is the Denton Holme region of Carlisle, and it's evident the effect of climate change has shown a fairly marked increase in areas of flood risk, where the darker blue shows the locations that are now in flood risk that were not in present day scenarios. Next slide, please. Similarly, there's results for London. It says 30 year in the title, but in fact, I think those images are for 100 years. I just realised that those are for Denton Holme again. So can you advance that slide on one, please? Okay, there are similar results for London, but it looks like the same Carlisle results have come in. This is results for Manchester, and a way in which we can interrogate some of the results a bit more than just showing the outlines of flood extent. So in this case, we can look at the percentage increase in depth, the percentage increase in velocity, and then a combined increase in hazard that creates. So we're looking at average values across those 4 locations of about 30% increase in depth and velocity, and 10% in the hazard index increase. So that's another way of examining some of the outputs. I think it's also true, and we'll talk about this at the end of the both of these sets of examples, so we'll see the results from Loughborough shortly, but it's also true that we can do a bit more from this analysis to work out the degree of impact it might have in other cases. So as well as just looking at depth and hazard and velocity, we can look at some of the actual monetary impacts or other societal impacts that it could cause as a result of these uplifts. Thanks. That's, I think, the last slide from me on work from JBA. I'll pass on to Xiadong from Loughborough.
Yeah, great. Thanks, thanks Hayley and thanks Murray. I'm Xiadong from Loughborough University. I'm pleased to present some results from the Loughborough team. Next slide, please. So we're going to use a hydrodynamic model called HyFIM to simulate urban flooding using the rainfall uplifts from the previous research. So before we do this work, we need to think why we use hydrodynamic model rather than like other quick models to do this work. So we are actually facing 4 challenges in urban flood modeling, and these 4 challenges can connect to 4 requirements of urban flood modeling. Firstly, we should consider extreme events. Some events are even kind of unprecedented in the future due to climate change. This requires our model more physically based rather than based on empirical models, empirical parameters, which calibrated a lot based on past events. And secondly is the complex topography on urban region because of the buildings and infrastructures. We need a high resolution model. The spatial resolution must be high enough to reflect these complex topography. And thirdly, in cities, we usually have a large domain, maybe apart from some small cities, like in cities in London, Manchester, we need to cover a large domain. This means we have a lot of computed cells in the model domain. And the third challenge is the human intervention. Sometimes we have new flood defense infrastructures like walls or pump stations or the improved drainage capacity. So these need to be reflected in the model. So 4 requirements for model stability, both for the model itself and the numerical methods must be stable enough to reflect the extreme events, the high dynamic events, and the accuracy, spatial accuracy, and temporal accuracy. And speed must be fast enough to finish the event, so that we can also provide flood forecasting rather than just simulation based on previous events. And flexibility, the model must be flexible enough to dynamically consider those human interventions. Next slide, please. So the urban flood modeling system we built based on a high-PIM flood model. High-PIM is short for high-performance integrated hydrodynamic modeling system. There are 4 features about this model. Firstly, it's fully physically based. So the governing equation of the model is it's full version of 2D shallow water equation. This guarantees that the model can reflect the actual physical process of surface flooding throughout the whole event. And secondly, the model uses state-of-the-art numerical scheme to calculate those partial differential equations. This guarantees the accuracy of the model. And the third part, the third feature is a very important feature. This actually bring the hydrodynamic model from small cases or ideal cases in the lab to the practice case, to the real world for large scale simulation using GPU rather than CPU to do the calculations, because CPU usually consists of a few cores which are suitable for complex tasks. But for parallel computing in millions of cells, to solve these partial differential equations, GPU is much more efficient and actually much more cheaper than the CPU. And the last one is the improved numerics methods developed just a few years ago by our colleagues in Loughborough. And these can solve some problem, some numeric stability problem and accuracy problem when we face fluid flooding in very steep topography, which is typical in urban regions. So these 4 features give the high-PIM model a very good condition to run to finish the task. Next slide, please. Yeah, next slide, please. Hayley. Yeah. So to set up the high-PIM flood model, we firstly need to consider about data. We need DEM data using high resolution. We can use the LiDAR data, 1 meter, 2 meter resolution, or the OSDTM data in 5 meter resolution. And we need uncovered data for some parameters like friction, infiltration, and drainage, if we don't have drainage and infiltration data. And we need crowdsourced photos to calibrate model to see whether the results can reflect the actual flooding happened in the city. And the rainfall input can be gradient-based inputs, for example, from the Nimrod radar observations, or it can be numerical weather predictions from the UKV model. And it can be also just one point for the whole domains we are going to use from the rainfall uplifts. So it's quite flexible for the rainfall inputs. And the parameters, according to the EA suggestion, they use 30% of reduction to rainfall and 12 millimeter per hour fixed value for the drainage capacity across the UK. And we tried different methods, but the EA suggestions also, we try to consider it more details, consider infiltration based on 2 different land cover, unpaved land and paved land, and the drainage only on the road surface rather than the other surface, because we assume that drainage networks are built on the roads rather than in the whole domain, and consider drainage capacity in different in city center and suburban region with different values. Next slide, please. Before set up model, we firstly need to generate the observations which are useful to calibrate the model. Use observations from cross-source data based on a few events and generate the flood extent. And we need to edit DEM to remove a few blocks over flow paths, such as overhead buildings and overhead bridges, over roads and over rivers. Next slide, please. So to calibrate model first, use different parameters and use to compare it with the compare our simulated results with observed photos. So this one example in Newcastle. We compare the one output of the model at exactly the same time with a photo taken by pedestrians, and the result match quite well. And next slide, please. This one also in Newcastle, just over on the main road in the north of the city center of Newcastle. So it also matched well. So after, next slide, please. After we calibrate the model, we can do the simulations. So the simulations, we run flood model, urban flood model in 6 cities across UK, including Newcastle, Glasgow, Manchester, Carlisle, London, and Rwanda. The areas are different. And resolution, we choose different resolution just to see what kind of resolution is kind of acceptable in a specific city. For example, in London, we use the 5-meter resolution. This means we have 64 million cells. It's quite a big number of cells, and in Newcastle, not only Newcastle, also considering the adjacent regions, including Tyneside and Gateshead. It's a greater Newcastle, and that's the largest domain we consider in terms of the number of cells, over 100 million cells. So the 4 simulation, the 4 cities, we do simulations based on these the resolutions that is in the table. Next slide, please. On the rainfall scenarios, we got input from the climate model, consider 2 return periods, 30 years and 100 years, and 3 durations of events, 1 hour, 3 hours, 6 hours, and 4 ensemble members of the uplifts. Actually, we also consider the current scenario without any uplifts as a baseline simulation, and those scenarios together means we need 30 simulations for each city and 180 in total. On the uplifts given to used to increase the flood, the rainfall predictions, rainfall values from based on the flood estimation and FEH handbooks web service. We got the value, and then we use the micro FSR formula to generate rainfall profile. The uplifts as well to add it to the profile directly. So I think this kind of answer one question asked before about how do we add the rainfall uplifts to actual events or to continuous events. This is a way we just added evenly to the rainfall profile. Next page, please. So the HyPIS model can produce flood depths at every time step and flood velocity at every time step for all the cells within the domain. And the time step, because the hydrodynamic model usually uses the self-adjusted time step, the time step is quite small. For example, the case in Carlisle, the time step is around 0.001 second. So literally, we can produce flood depths and the velocity maps for every second of the event. So this map shows the maximum water depth of the research domain in Carlisle, and just based on the 1 or 100 year return period simulation, and you can compare the different uplift scenarios in this map. And next page, please. So we just show a few results. There's not all the results, just the result in Newcastle, Tyneside region. And this for 6 hour 100 return period events. The uplifts are also indicated in the legend of the map. Next slide, please. This one is for London, the Great London. This 3 hour 100 return period events. And next, please. Yeah, so this just maps, and we also made some quantitative comparison between the results. We care about what kind of change we can see from the rainfall uplifts to the actual flooding on the city. So we compare the flooded cells in the domain, but not all flooded cells, only the flooded cells in the urban and suburban region, actually the built-up region where people live there. We don't care about the increase of flooded cells in lakes or in rivers or in regions with no people living there. So we compare the flooded region, the air with the current results without any rainfall uplifts, and with a few different rainfall uplifts from the climate model at different water depth level. This results in Carlisle for 30 years return period events. Next slide, please. So this is another result from also for Carlisle, 1 over 100 years. We can see that the rainfall uplifts, for example, rainfall uplift one is 25%, and we can see the inundation increase is actually much larger than the 25% for every flood depth level, which means the uplifts of rainfall is exaggerated in the inundation. So next slide, please. And we make the similar comparison for all the 6 cities. For example, it's a result for 1 over 100 year return period, and we choose the flood depth rank as inundation larger than 0.3 meter, and for different rainfall uplift scenarios, return 25%, and the least increase in Rwanda, still 40% more area flooded by the rainfall events. And the next page also, so this kind of give us a general conclusion for this part, the hydrodynamic modeling and the rainfall uplifts due to climate change is kind of exaggerated in the flood simulation, and we will expect more serious flooding in the future because of the rainfall uplifts. And I will let Murray to give a final conclusion about all the flood modeling work in the final page. Thanks.
Thank you, Xiadong. That was very good. There's just one slide to draw together a bit the results from the 2 groups who've been carrying out this modelling, JBA and Loughborough University. Some of the sort of headline findings, perhaps, that may help people focus on what this is telling us and where it might go following this project. So both organisations' results indicate that there'll be increased flood impacts in urban areas in all the areas that we looked at as a result of the changes to rainfall. Different input data and modelling methodologies have been used in each case, and they result in, to some extent, or largely unexplored variation in the results. That's something we could look at, that the degree to which input data and the method in which you carry out the modelling results in changes. The maps that show extent of flooding changes and also velocity and hazard may not tell the full story in terms of the impacts that are resulting from these changes to rainfall in the future. So more in-depth analysis could point to impacts related to properties, critical infrastructure affected, damage costs, and also this role of modelling methodology playing in estimating the impacts. And those are things which are under consideration at the moment with the project team, and considering how further work in that area might be put forward in proposals for further research. Thanks very much. We're very happy to take questions in this section on the modelling output. And also we're happy to take questions on the rest of the project, so the first part of today's webinar as well.
Great, thanks very much, Murray. I'm chairing this next session of Q&A, and I can see we've only got one question. Oh no, look at that. Questions are pinging in now. We had a question about flood damages to start with. I think you touched on this in your final slide, Murray, but I mean, I suppose what would be interesting is given the, I mean, it's very much a preliminary study looking at 6 cities. There wasn't a whole load of resource attached to this piece of work. Most of the project actually concentrated on the actual generation of the uplifts themselves. So, I mean, what do you think would be the next stage in this? Fergus talks about flood damages, perhaps looking at that. But he also asks another question. Have you looked at the differences between the JBA and the Loughborough outputs as well?
Yes, I don't think we have looked at the differences particularly. We've only recently been able to share these between ourselves and during the project lifespan. So I think there would be opportunities to consider how the different methodologies and approaches come out with the results they do, and they could be quite complex, the reasons for that. Just on the first question, I know I did touch on it, the effects of flood damages. I wonder if my colleague Rob might want to say a word on that, because there are tools available that can assess damages in surface water flooding cases, and Rob, I know you've been involved in those as well.
Yes, that's true, Murray. I mean, we've talked about tools that we have in-house. Obviously, there are various studies that have computed impact metrics from surface water flooding, and I guess that perhaps the most comprehensive analysis that has informed outputs in the public domain would be for the National Security Risk Assessment 2017 inland flooding scenarios, where a large number, more than 100 if I remember rightly, impact metrics were computed from surface water flood depth grids of the type that you've shown in the presentation.
I think, Neil, do you want to say something as well?
Yeah, thanks, Hayley. Sorry, just to add to Rob's points, I guess one of the challenges of calculating damages in these types of surface water flood models, where the depths are sort of quite shallow and we've got different ways of representing the buildings within these models, is that actually extracting a representative depth to apply the various depth damage curves that are available is, adds quite a lot of uncertainty to the process as well. So it's certainly something we can do, and is a useful metric into comparing models, but almost there's as much uncertainty in how you extract that representative value, which is sensitive to modeling methodology, that could skew the results. So I think it would be very useful to look at, but we do just need to make sure that we're comparing light with light when we do it.
Thanks, Neil. So a few more questions coming in. I guess this is one for you, Murray, or for JBA perhaps. Maybe it's for the Environment Agency. Will these model results be put into the Environment Agency's risk of surface water flooding online?
I mean, from our side, as you said, Hayley, this is an experimental project looking at how you might translate these rainfall uplifts into impacts on the ground with regard to surface water flooding. So obviously there are impacts for the water industry related to sewer flooding and spills from CSOs and pollution. There's also this impact on general surface water flooding and flood risk in urban areas. So it was the project was looking at how this could be done and picking some key locations. And I think with results of this, the outputs of this could influence decisions as to whether there might be some discussion around doing that. But it's, obviously in the Environment Agency's remit to consider that. But also in terms of that question about the ABI, was this shared with the ABI? I don't believe it has been, but I think it would probably be of more use to the ABI to see something on a national basis than just for a few trial locations.
Yeah, absolutely. So, I mean, the next stage in this would be to, I suppose, looking at all the different uncertainties, it's actually quite difficult to design for future flooding. Given what models you use, what scenarios you use, all of these provide uncertainties. But looking at the national scale would be very useful, I think, as well. So we've got a question from Sven Berenson, who asks, in hydraulic, but also applicable to hydrological modelling, building locations and numbers as well as land use tends to be taken as fixed when looking at future scenarios. Are there plans to take future changes in this into account, as well as to assessing the possible impacts? I don't know who wants to answer that, from Murray or Xiadong. Xiadong?
Yeah, I can answer this question. Thanks, Swan. So this, it's a very good question. Actually, this question is kind of, if we did consider the future change it's kind of more suitable for catchment scale rather than city scale, because the climate change, the impact of climate change on land cover will be huge, and this will actually change some parameters of the model. But in cities, kind of, the uncertainty is huge. It's more related about like the human activity, the city plans, and the other activities. So we definitely can try different scenarios. For example, the increase drainage capacity, or a new plan for like new developing regions with new buildings, and those kind of factors. But as long as we have enough data to assume those parameters, I think that is my answer.
Thanks, Xiaodong. Oh, did you want to say something, Murray?
Only that we perhaps need to consider the uncertainties with relation to the rainfall and the modelling as well in the round when you're considering things like this about the impact of individual structures and buildings. You can model everything, but it's good to keep an eye on where you're getting the uncertainties. If you're getting massive uncertainties in one area, it may not be worth considering things on very fine scale in others.
Thanks. Another question for Xiaodong from Fiona McClay. Can you provide more information on how you used crowdsourced photographs for model calibration validation? Is there a lot of manual work in identifying locations, time, date, etc.?
Yes, that's right. It's a lot of manual work, but this can be done by, as far as I know, I did read some literatures, and some people are doing this work to use machine learning methods, analyze the crowdsourced photos with videos and with the OpenStreetMaps or Google Maps, Google View, Street Views to generate flood extent. But this cannot be on my subject. And I'm also hoping some people can do this work, and this work this will help us to calibrate model much easier in the future.
Great, thank you. And a question from Chris Parker. So it's given that with climate change, return periods or levels are dynamic and constantly changing, would it not make more sense to run a range of rainfall depth events in hydrodynamic modelling rather than return periods? I understand why this is done, but I think going forward, this would be more useful. Any comments from anyone?
I can respond on this, and maybe others want to chip in. This is quite similar to the comment in the previous session about how useful are return periods in this situation, and that was perhaps more related to non-stationarity, but I think it's a similar issue. Traditionally, we've been assessing flood risk with discrete events. So we follow this approach where we use one rainfall event, you make some assumptions about how wet it's been and how wet the catchment is, and then you make your systems robust or resilient to cope with those return period estimate events. clearly there are issues with that about clustering of events and storage in systems and so on, which mean that that discrete event approach is flawed to many degrees. But the benefits it has is that you can design levels of service to manage an event of a specific return period. And when you're trying to, yes, you can run time series simulations that are perturbed for future climates with rainfall and catchment conditions, but it then becomes a serious challenge as to how you derive systems that have a level of service that shows that they are resilient to future climates. So when you've got a 100-year storm, you can say you built a defence that copes with a 100-year, can manage the water levels within that 100-year flood. That's relatively straightforward. But if you're trying to then say, we've done lots of different future time series simulations with climate change adjustments, and we've made them robust to 5 or 10 of them, what level of service have you then got? It's not easy to work that out. So there are big sort of engineering and policy level questions to answer if you're going to go down more scientific estimates. But having said that, the water industry are doing this with this REDUP tool that we're developing for them, it's particularly for CSO spills, but also there are catchments where this is being considered for time series simulation, such as the Thames at the moment with the Environment Agency. So it's a complex area, but I think it's going to be very difficult to leave alone the design storm approach anytime soon.
Yeah, Chris has come back with, but you could infer those levels based on what events you've run. And he's right to a certain extent, I think.
Yes, but again, how confident are you that you've captured the future effectively in a way that you can assign rarity to those situations? Because you can set it up with lots of 100-year events or a 500-year event and then nothing for a while. How realistic is that? How realistic is it to have long intra-event dry periods, etc.? So I think there are still questions to answer if we're going to move away from the design storm concept to how you make systems resilient from a consistent level across the country. I'm sure the Environment Agency and others might have comments on this as well. So that's just my personal view.
I think I can talk a little bit about the question by Chris. Actually, we are doing that work. We actually use rainfall depths, but just we connect them with the with return period. But you definitely can just directly use water rainfall levels at different depths, because we for example we run 30 simulations for each city. Those 30 simulations, each simulation has different water rainfall depths, or we call rainfall the total amount rainfall, and we use that to produce a rainfall profile. So you can definitely find that, and you can even kind of create a curve between rainfall inputs and the flood inundated area. So it's just actually our work. We have done that.
Thank you. I mean, I think there's a whole load of questions. Perhaps future drainage has provided some of the answers, but there's a whole load of questions that still need to be resolved. I mean, something we haven't talked about at all today, but something that one of my PhD students has been working on, Roberto, is looking at storm profiles and trying to update the FSR as well, which obviously hasn't been updated since 1975. It's quite a long time ago, and really thinking about what do actual storms look like. And it's not always like the FSR profiles. So we've been working with JBA recently to try and come up with a set of storm profiles that people can start to use in design, which we'll try and release at some point. But very much research, but I think ties in with what's needed in design. So we do need to rethink flood estimation methods, but we can't solve every problem at once. So I don't see any more questions from anybody in the Q&A. And so I think we're about 5 minutes early finishing, but that's fine. If there's no other questions from anybody, I will tell you that Suraj asked me to say that there is another webinar next week from the Climate Resilience Programme, and that's actually the last one of the series at the moment, or the last one of the season. And you can see on the screen there that that's actually next Wednesday from 12 till 1. And Professor Martin Evans from the University of Manchester and Tim Thom from Yorkshire Peat Partnership talking about understanding the microbial communities of resilient peatlands. So thank you all for attending today, and I hope you found it interesting and useful, and hopefully we'll get to do some more work in this area together with all of you. So thanks very much.